My name is Kenshi Lu, and I'm happy to be here presenting this work called Generalized Optical Flow-based Motion Vector Refinement in AV1. As a summary, basically this is a new coding tool in the AV1 codec. The main idea is to refine motion vectors for each subblock within a prediction block. The refinement is done based on optical flow equation, and it can be regarded as an extension of the bidirectional optical flow method. The outline of this presentation is as follows. First, I will present the motivations and some background of the method called BDOF. Then I will show how we extend BDOF for AV1 compound prediction. Then I will introduce how we implement the experiment in AV1, and finally some experimental results. For motivation, we consider that in interprediction, typically we define and signal the motion vectors for each prediction unit. In this way, in practice, even after the motion compensation, there may still be remaining motions needed to be compensated. For example, there may be occlusion within a prediction unit, or we may have some camera zooming or camera motions that are not translational or not uniform. So in these cases, it is desirable to have motion vectors at a finer granularity to be able to compensate those non-uniform motions. So the goal here is to estimate pixel-wise, or more practically, subblock-wise motion vectors within the prediction unit. And the compound references would be useful information to get such motion vector estimates. So here's a brief introduction for how bidirectional optical flow works. We first consider the current block and denote it as cur. We let P0 and P1 be the bidirectional references of current block after motion compensation. We assume P0 is from the past and P1 is from the future, and they have the same temporal distance to the current block. So in the motion compensation, the motion vector would characterize the motion for the whole block. However, it may not exactly characterize the motion for each pixel. Say if we consider one pixel in the current block, there may be some remaining motions we would like to apply on top of the original motion vector. So we denote it as Vx and Vy. We denote this fine motion associated to P0 as Vx and Vy. And in this way, if we assume that this fine motion is steady, the other fine motion with respect to P1 would be minus Vx and Vy. Then the optical flow equation comes in that says Vx and Vy will follow this equation. And in practice, this temporal derivative can be estimated using temporal distance between cur and P0, or between cur and P1. And those spatial derivatives could be estimated using numerical gradients in P0 or Py. So the only unknown variables would be the fine motion Vx and Vy. And starting from the optical flow equation, we can apply it to P0 and Py to get two equations and subtract them to get the equation below. As I mentioned previously, everything in this equation except Vx and Vy are available. They are available to both encoder and decoder. So this equation is defined per pixel, but in practice, we can define it for each 4x4 or 8x8 subblocks. So if we consider a 4x4 subblock, there are 16 pixels. So there are 16 equations like this and 2 unknown variables, Vx and Vy. In this way, we can solve a least square solution to get the fine motion. So this is how BDOF works in VVC. In VVC, we consider 4x4 subblocks. So we have a least square of 16 equations and 2 variables. The closed form solutions are given in the right. And once we get Vx and Vy, we can refine the motion vectors for each subblock like this. And then we can apply a second pass of motion compensation for each 4x4 subblock to enhance the interpretation quality. That's how it works in VVC. And now if we were to integrate this tool to AV1, there are several generalizations we need to make. First, the AV1 compound prediction can be either bidirectional or unidirectional. For unidirectional, it means that the 2 compound references could be both from the past or both from the future. It's not necessarily one from the past and one from the future. And second, the temporal distance to the 2 reference frames may not be equal. So in order to make this generalization, we define the side temporal distances from P0 or from P1 to Kerr. We denote them as P0 and P1. And it means that if the reference is from the past, then the D is positive. If the reference is from the future, then D is negative. In this way, we can look at the figure below. It tells us that when the temporal distances are not equal, actually all we need to do is to make the magnitude of the fine motion proportional to the temporal distance. So the fine motion associated to P0 would be V0, Vx, and Vy. And that for P1 would be D1, Vx, and Vy. Here I show another example where the 2 references are both from the past. The fine motion would follow the same rule. And if the 2 references are both from the future, the result would be the same. So with the generalized expression of the fine motions, we go through all the derivations in the optical flow formula and consider K by K subblocks, where we have K-square equations and 2 unknown variables. The closed form solutions are given here. The only difference is that in the Gx and Gy, they are in terms of D0 and D1. We also do the refinement of the motion vector based on the fine motion. And I would like to mention one special case, that is when D0 is 1 and D1 is -1, it reduces to the traditional by prediction as in the VVC scheme. This is how we implement it in AV1. We consider an anchor in the experimental branch with config new intermodes. This config is actually a cleanup change that reduces the number of compound modes. So we decided to implement on top of it for simplicity. We call our new experiment config optical flow refinement. And there we introduce 5 extra compound modes called near MV optical flow, etc. It turns out that there are totally 10 compound modes in this experiment. Because there are many more compound modes, we simplify the RD search in many places. For example, we disable OBMC and warped motion in the new modes we introduced. We also remove the search of interpolation filter and always set it as a sharp filter. We also remove the search of compound average type and always use a weighted compound average, which I will mention later. Some implementation details. For gradient computation, this is a figure for illustration. Say the black dots are the pixels in the original interpredictor. Now for each pixel like this one called ij, we will need the 4 pixels in green around it in the left, right, top, and bottom. And we apply a Sobel difference operator to get the gradient. For example, the x gradient would be the right green pixel minus the left green pixel divided by 2 delta. And the same for the vertical gradient. In this experiment, we set delta as 1/8 pel. This is how we get the numerical gradient. Some other implementation details. First, this method can work for both luma and chroma. So we refine the MVs for both luma and chroma. We also enhance the precision of the refined MVs from 1/8 pel to 1/16 pel. This is helpful because the MV offset or the quantity of the MV refinement could be small in many cases, especially for smooth regions. And this helps the prediction quality. We select the block size based on the prediction unit size. In particular, we use 4x4 subblocks if the prediction unit is smaller than 16x16. We use 8x8 subblocks if the PU is greater than 16x16. The intuition behind this is that we would like to have motion vectors at finer granularities, especially when the prediction unit has more fine details or more detailed video contents. And it is more likely to have more fine details if the prediction unit size is smaller because of the RD search. We apply a distance-based weighted compound average. That is, we have this weighted average of the 2 refined predicted blocks. And the weights W0 and W1 are defined this way. This has been heuristically determined in the AV1 code base, and this is also used in baseline AV1. Some experimental results. The baseline is new intermodes and the test config is optical flow refinement. We run the test on 3 test sets, which are called low res 2, mid res 2, and HD res 2. Each test set has 50 clips, and we encode 150 frames at 6 different quality levels for each clip. The gain in PSNR is about 3%, and similar gain is observed in SSIM. The encoding time is increased by about 40%, while the decoding time is increasing between 45 and 55%. And finally, I just want to mention some speed up methods and the future work. As I mentioned in the gradient computation slide, we need some motion compensation process to get the gradient. So we can also consider instead doing interpolation on the original predictor, like bilinear or bicubic interpolation, then we can skip some motion compensation processes. Also, we can solve the least square with fewer samples. For example, a Queen constant sample block, which gives about 5% speed up in decoder side with 0.25% quality loss. And finally, we can optimize the code with SIMD. And that's all for this presentation. Thank you.